Hello guys, welcome to chapter 5. Today we start with spectral theory, and this is the part where functional analysis meets complex analysis, and it's gonna get very interesting in the time to come. And basically what we would be talking about is the concept of eigenvalues, spectral values, spectral set, and this is where we would use concepts from complex analysis and prove theorems and do further analysis on infinite dimensional spaces. So without further ado, I would like to start talking about spectral theory. So we start with a complex Banach space this time. Now one thing that you need to understand was that, well, in number theory or in school you learn that every real numbers, so this is the set of real numbers, blah blah blah, and you saw that all these real numbers can also be characterized or can also be put in the set of complex numbers, because if you ask me, one is also real and one is also complex, where the complex part iota is 0. But in spaces the structure is a bit different, so every complex space is also a real space, because by a complex Banach space I mean that the scalars that you used to always see that, okay, any vector space is where the laws of scalar multiplication and vector addition hold true. So now we have the complex Banach space. So what I am saying is, when you multiply with a scalar any element v1 of the complex space, then what you get as a result is also belonging to the Banach space. But in complex Banach space, the scalar can be a complex. That's the basic definition of a complex Banach space, that everything remains the same as was in the case of real space, but when you multiply these scalars, then those scalars can be complex, and then my space can be characterized as a complex Banach space. So I have X, which is my non-trivial complex Banach space. Non-trivial just means it's not 0. And I have T, which is defined from dt, which is a closed subset or a subspace of X to X, and this is a linear transformation. Okay, so the resolvent set of T is the set. So what is the resolvent set? So it's the set of all lambdas belonging to C such that lambda I minus T inverse is an operator from X to X. So now a very important thing that we need to note down here is that when I want to say that there is a lambda which belongs to my resolvent set, so I have Banach space X, and from this space there is an operator lambda I minus T inverse, which is going from X to X. Okay, so I am saying that lambda I minus T inverse should be an element of the space of continuous functions from X to X. If this holds, so I am putting all such lambdas where this quantity is an element of this space into my resolvent set. So resolvent set is the set of all lambdas belonging to complex numbers such that lambda I minus T inverse belongs to LXX. Okay, now R lambda T is this operator. So this operator is often referred as R lambda T. It's called the resolvent operator. And now the spectrum. What is the spectrum of T? The spectrum sigma T, the numbers in sigma T are called the spectral values. And what are the spectral values? Well, complex, complement, resolvent. So if I have any lambda, it either belongs into the resolvent set or it belongs to the spectrum. There is no other place where it can belong, because if you union all the spaces, it's the whole of C. So till now what we have done is just the definition of the resolvent set and the definition of the spectrum, and we see that, okay, it's the set of all lambdas such that lambda I minus T inverse belong to LXX, and it's the set of all lambdas, so sigma T is C complement resolvent. So now we prove a lemma. We say that let X be a non-trivial complex Banach space, and our operator T is defined from dt to X, and it's linear. Now I say that if T is not closed, then the spectrum is all of complex numbers. Now let's philosophize it. I say that if the operator is not closed, so as I saw above, I say that a resolvent is the good set because for those values of lambda I minus t inverse exist and is bounded. Well, of course, if it's belong to LXX, then I just needs to prove that it is bounded. Even the existence is not needed to prove. So what I am saying is, I would say that the spectrum is the bad set and the resolvent is the good set. Now, if I'm saying that if the operator is closed, then the spectrum is all of complex numbers. I do not have anything in the good set, which is a bad thing. Well, so now coming on to the proof itself, I would say that, okay, so here I'm saying that if T is not closed, then the spectrum is all of complex numbers. Now I say that let T be closed, and we show that T is closed if rho T is not equals to phi, which means that saying that there is a lambda which belongs to rho T. And if I can prove that, then I can show that if T is not closed, then sigma T is equals to all of complex numbers, because when the resolvent is non-empty, then T is closed. And this is what I'm trying to prove. And once I prove that, then I can see how the inverse operation holds true. So now Seth, let's take a lambda belonging to the resolvent set, which means that lambda I minus t inverse belongs to LXX. Because that's what was my definition was. So, you know, I defined it like this. I say that, okay, T is defined from domain of T to X, and resolvent is the set of all lambda such that lambda I minus t inverse is from X to X. Now, let Xn be a sequence with the property that Xn tends to X and Txn tends to Y as n goes to infinity. So it is given, you know, I am given a sequence which converges to X and Txn which converges to Y as n tending to infinity. Now when I take the limit, so I know that T goes from dt to X, therefore lambda I minus t also goes from dt to X, and therefore lambda I minus t goes from, okay, now this is not how I write goes from, so this goes from dt to X. So lambda I minus t inverse of something in X should be like, you know, lambda I minus t should go from X to dt. Let's fix this. Okay, now I say that, okay, I take limit of lambda I minus t xn. I say that it is equals to lambda x and y, because txn tends to y and xn tends to x. Now I take the inverse of this. I take lambda I minus t inverse, I pre-multiply by lambda x minus y. Now this was, so lambda I minus t took something from dt, this was in dt, to something in x, and thus the inverse takes something in x to something in dt. So this was in x, and lambda I minus t inverse takes me back to dt, so this thing belongs to dt. Now I use in this step the property that lambda I minus t is continuous, because I can write lambda x minus y as limit n tending to infinity lambda I minus t xn. And since I know that lambda I minus t inverse is continuous, I can take this inside and I am remain just with x. So till this time I prove that, okay, lambda I minus t inverse lambda x minus y is a member of dt and dt on both hand sides. So I have now proved what? I have proven that this x belongs to dt. Okay, and I recall the definition of closed. I say that if there is a sequence xn in dt such that xn converges to x and txn converges to y, then if t is closed, I can say that tx is equals to y with x belongs to dt. So I have proven this part already. I need to prove this one. But if you look at this equation, lambda I minus t inverse lambda x, so I have written it here again, lambda I minus t inverse lambda x minus y equals to x, and I multiply both sides by lambda I minus t. So I would have been remained with lambda x minus y is equals to lambda I minus tx. Now if I just compares the value term by term, this is lambda x, lambda x, and this is y, and this is tx. So I can say, looking at this, that tx equals to y, which implies that t is closed, and this is what I wanted from the beginning. So this is it for this proof, and this is just some sort of explanation I wrote it myself when I was looking at this proof for the first time. So I just wrote here that we are trying to invert lambda I minus t. So look at the equation. When f is given, you have to find u. If you can find u uniquely, then lambda I minus t must be invertible, and that is what we used in this. Now let's look at some definitions. These are the definitions of the spectrum, and I start with saying that let x be a non-trivial complex Banach space and t be defined from dt to x. It's a linear transformation. Now the point spectrum of t, okay, again it's all sets, and it's absolutely important for you to open up your eyes, ears at this time, because we're going to use this definition again and again and again and again. So make sure that this is ingrained in your soul. Let's start with defining the point spectrum. We say that the point spectrum of t is the set such that all those lambdas belong to the spectrum such that lambda I minus t is not injective. Now what I saw before, that lambda was belonging to spectrum, which means that, okay, when lambda belongs to the resolvent, so lambda belongs to resolvent implies that lambda I minus t inverse belongs to Lxx. And now I am saying that lambda belongs to the point spectrum, so I write a small p there, if and only if all those lambda belong to the set of sigma t, or to the set of such that lambda I minus t is not injective. Okay, this is a definition. We just need to remember it, ingrain it, tattoo it. So a number lambda belongs to the point spectrum is an eigenvalue of t, and the space E lambda, which is the space of kernel of lambda I minus t, is the corresponding eigenspace. Its dimension is the geometric multiplicity of the eigenvalue, and non-trivial elements of kernel lambda I minus t are eigenvectors or the eigenfunctions. So a lot of things to unfold here and to unwrap here. Now I'm just saying that there is an operator t, and a point spectrum is the set which consists of lambdas such that lambda I minus t is not injective, and I say that the kernel of lambda I minus t is the eigenspace, and its dimension is the geometric multiplicity of the eigenvalues. So I would talk about geometric multiplicity when we discuss compact operators and self-adjoint operators. As of now, I just want to say that geometric multiplicity is the dimension of the kernel of lambda I minus t, and kernel of lambda I minus t is also an eigenspace. Okay, and the geometric multiplicity can also be thought as the number of linearly independent eigenvectors in the kernel of lambda I minus t. And now I talk about the continuous spectrum of t. It's the set such that lambda I minus t is injective and not surjective. Okay, injective, not surjective, and the image of lambda I minus t is dense in x. So this is a way of writing that image of lambda I minus t closure equals to x means that the image of lambda I minus t is dense in x. So what was continuous spectrum? It is the set such that lambda I minus t is injective, not surjective, and the image is dense in x, image of lambda I minus t. And the third is the residual spectrum, the set of all lambdas belong to sigma t such that lambda I minus t is injective and not surjective, and the image is not dense in X. So this is the crux of these definitions. Now I would go to some remark. Suppose that T is closed. Now I know that the closed graph theorem tells me that X and Y be Banach spaces, and T is closed, then and T is closed and linear, then I say that T is continuous. And similarly here, I know that if X and Y are Banach spaces and T is from dt x to y, where dt is a subset of X, I say that T is closed, linear, and it's a bijection. Then I say that T inverse is continuous. So, well, as soon as I have closed and linear, I can say that T is continuous rather than being closed, because that's the closed graph theorem. And once I have that T is continuous, then the inverse mapping theorem shows me that the inverse mapping from y to dt, so I will write T inverse y to x. I've written it before also, but I'll write it again. So T inverse y to x, T inverse y to dt, and then I from dt to x is continuous, so T inverse is continuous. Similarly, that's the argument I'm saying here. I'm saying that lambda, suppose that T is closed, so lambda I minus T would be closed, and I say that lambda I minus T from dt to x is a bijection. So if I can see here, the mapping is from x to x, so that makes things easier for me. Now why am I saying that it is continuous if it's a bijection? Now you see that lambda I minus T is closed, it's linear, and if it is a bijection, then from here I can say that lambda I minus T inverse is continuous. That's exactly what's the argument that we followed here. So I say that if T is closed, linear, and bijection, then T inverse is continuous. And similarly here, it is already closed and it is linear, and if it's a bijection, then it's continuous, the inverse is continuous. So finally I would like to say that here I saw that for closed operators, if R lambda T exists, so R lambda T exists meaning that this lambda I minus T is a bijection. As soon as I say that lambda I minus T is a bijection, I say that it exists, that the inverse exists. And I say that if it exists and T is closed as an operator, then it is bounded. That's what the summary of this remark is. And in the next remark, I see that suppose X is finite dimensional, then the injectivity of T going from X to X implies the surjectivity of T. So the sets, the continuous spectrum and the residual spectrum are empty. So why does this happen? So if I know that from the rank nullity formula, this is applicable for the case of finite dimension only. So if you see this formula, that the dimension of kernel of T plus dimension of image of T is equals to the dimension of X, and I say that T is surjective if and only if T is injective. And the way I prove this is I say that suppose let T be injective, then the dimension of kernel of T is 0, and if the dimension of kernel of T is 0, then the dimension of image of T is equals to the dimension of X, and if the dimension of the image of T is equals to the dimension of X and image of T is a subspace of X, then image of T must be equals to X. And similarly, if I say that okay, T is surjective, then the dimension of the image of T would be equal to the dimension of X, and hence the dimension of kernel of T would be 0. So hence I can say that T is injective also. So it's a if and only if. And now I can say that since it's if and only if, so this case cannot exist, that lambda I minus t is injective and not surjective. So similarly in residual spectrum this case cannot exist. So if x is finite dimensional and t is, well, basically in finite dimensional case, the continuous spectrum and the residual spectrum are null and empty sets.